In automotive coating systems, the Clearcoat is often perceived as a purely aesthetic layer, responsible only for gloss and visual depth. In reality, the Clearcoat is a highly engineered functional layer that defines the vehicle's long-term appearance, chemical resistance, and environmental durability. Its performance extends far beyond surface shine. From a formulation perspective, Clearcoats are designed to withstand continuous exposure to ultraviolet radiation, temperature cycling, moisture, chemicals, and mechanical abrasion. Resin chemistry is selected to balance hardness with flexibility. Highly cross-linked networks improve chemical resistance and scratch durability, but must retain sufficient elasticity to avoid cracking under thermal and mechanical stress. UV resistance is a primary function of the Clearcoat. Ultraviolet absorbers and hindered amine light stabilizers are incorporated to protect both the Clearcoat itself and the underlying base coat pigments. Their effectiveness depends on uniform distribution and retention within the cured film. Solvent evaporation and film formation must ensure these additives are properly incorporated into the polymer matrix, rather than migrating or volatilizing during bake. Chemical durability is governed by crosslink density, polarity, and film compactness. Clearcoats must resist fuels, oils, acids, detergents, and environmental fallout. Solvent balance influences early film density and pore formation. Rapid solvent loss can trap microvoids that later act as pathways for chemical ingress, reducing stain and etch resistance. Scratch and mar resistance arise from a carefully engineered viscoelastic response. The Clearcoat must dissipate mechanical energy rather than fracture or permanently deform. Resin architecture, cross-link distribution, and additive selection determine whether scratches remain superficial or penetrate the film. Excessive hardness improves initial scratch resistance, but accelerates brittle failure and long-term gloss loss. Surface formation mechanisms strongly influence appearance. During flash-off, solvent evaporation controls leveling and surface smoothness. Early viscosity rise freezes surface texture, increasing orange peel and reducing DOI. Extended flow improves leveling, but increases the risk of solvent popping if diffusion pathways close too quickly during bake. Cross-linking kinetics during curing define final film properties. Inadequate cure leaves the film soft and chemically vulnerable. Overly aggressive cure increases internal stress and microcracking. OEM bake schedules are therefore tightly specified, and Clearcoats must perform consistently across allowable temperature and time variations. From an OEM qualification standpoint, Clearcoats are subjected to rigorous weathering tests, including accelerated UV exposure, humidity cycling, thermal shock, and chemical resistance evaluation. Appearance metrics, such as gloss retention, haze, and DOI, are tracked over time rather than measured only at initial application. Clearcoat robustness is evaluated at minimum, nominal, and maximum film builds to ensure durability across production variation. A Clearcoat that performs well only at ideal conditions represents unacceptable risk. In summary, Clearcoats are multifunctional engineering layers that provide UV protection, chemical resistance, scratch durability, and long-term appearance stability. Gloss is merely the visible outcome of a complex balance between solvent evaporation, film formation, and cross-linking chemistry. If you have technical questions related to Clearcoat formulation, UV degradation, scratch resistance, or OEM weathering failures, share them in the comments for discussion in future episodes.